Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of a unit thermal properties of matter. So let's begin with today's class. In the beginning, we are going to discuss about the thermal expansion and let's begin with the coefficient of the linear expansion. So its coefficient of linear expansion. The situation would be something like this, that let's suppose we have a certain road. This is the road, and this road is being heated by certain source of energy. So when solid is heated, the increase in length of this solid is what we call as the linear expansion. Yes, the ratio of the increase in length of a solid per degree rise in temperature to its original length, that we call as a coefficient of linear expansion. Basically, the thing is that let's suppose this is a solid rod and this is having a length of L. So when I'm going to heat up this solid having a change in the length which is directly proportional to its original length, which is directly proportional to the change in temperature that we have provided. So this is going to depend on these two factors. And when I'm going to write this in a single relation, that is equals to delta L is equals to alpha L delta theta. This alpha, which is a ratio of delta L by L delta theta, this is the coefficient of linear expansion of the solid. This is alpha. Yes, I hope this is clear. It's the ratio of increase in length, that is delta L of a solid, per degree rise in temperature to its original length. That is what we call as the coefficient of linear expansion. I hope this is clear. Is it clear? Now look at this. Look at this. We are having a two roads. One is of length 5 meter and another is of 10 meter. When this is of 5 meter and when this is of 10 meter, let's suppose both roads are heated for the equal time. So let's say that this road A has been heated from 10 degrees Celsius to 100 degrees Celsius. This is just the situation of change in 90 degrees Celsius, while here it's a case of 10 degrees Celsius to 200 degrees Celsius. This is 190 degrees Celsius. Both have been heated for equal time, but their degree rise or the change in the degree rise will be the different one. I hope this is clear. Is it clear? So their change in length definitely would be a different one. Now let's understood this analytically, that let's suppose we understood that L1 and L2 are the lengths of the road at two different temperature. One is at T1 degree Celsius and another is the T2 degree Celsius respectively. And the rise in the temperature of the road, that is equals to T2 minus T1 degree Celsius. Then coefficient of linear expansion alpha was equals to delta L by L delta T. So when I say delta L, it is basically a change in length. So it's a final length L2 minus initial length L1. This is L2 minus L1 divide by original length L that I have taken as an L1 multiplied by delta T. This is the change in the temperature. This is equals to T2 minus T1. So this is alpha, which we can say it's an L2 minus L1 upon L1 into bracket T2 minus T1. SI unit of alpha, let's look at this. It's alpha, that is equals to delta L by L into delta theta. You can use the symbols as per your convenience. If you want to write it delta T, you can use it. If you want to write it delta theta, you can use it. So if I go for the unit, let's look at this. For unit, this delta L 4 meter, this L 4 meter, and this theta is for Kelvin. So this meter could be gone and it's a 1 by Kelvin inverse, or we can say it's a centigrade inverse. Dimensional formula of alpha, it's an m0 l0 t0 k to the power minus 1. It's a 1 by Kelvin. I hope this is clear. Now this coefficient of linear expansion of a solid, this depends on the nature of the material and the scale of the temperature. So as it depends on the nature of material, every different material have a different alpha. Let's look at this. We can say iron having an alpha of 12 into 10 to the power minus of 6. Copper, it is having an alpha of 17 into 10 to the power minus of 6. Brass, it is having an alpha of 18 into 10 to the power minus 6. This is all are of per degree Celsius. So, so we understood that now from this that the linear expansion of a solid depends on three factors as we have discussed. It depends on its original length, it depends on the nature of the material, and it depends on the change in the temperature. So we can write like this. It's a final length. Let's call it as an L2. This is equals to L1 into bracket 1 plus alpha T2 minus T1. This is L2. So this, if you want to write the change in length, if you want to write change in length, that you can have, it's an L2 minus L1, or you can say this is delta L, which is equals to alpha L1 into T2 minus T1, and the final temperature T2, that is equals to L2 minus L1 divided by alpha L1 plus T1. And if you want, it's a percentage change in length. This is equals to delta L by L into 100 is equals to alpha into delta T multiplied by 100. So always remember this relation, and from this you can have everything. It's a delta L is equals to alpha into L into delta T. I hope this is clear. If you remember this, every of these things can be derived very easily. I hope this is clear. Is it clear? Great. Now let's look at certain quick questions. A substance having very small coefficient of linear expansion is, this is the information based question. Invar is having very small coefficient of linear expansion. Please do remember this. Next, a thick glass tumbler gets cracked when boiling water is poured into it. Why? Because this is of unequal expansions. Yes, that's why it is going to be breakdown, or it is going to be cracked down. I hope this is clear. Is it clear? Is it clear? Is it? Are you sure? Great. Now let's understood that coefficient of areal expansion. This is even known as the superficial expansion. This is also called as the superficial expansion. So let's look at this, what it is. Let's have a look. First, it's a coefficient of areal or superficial expansion of a solid. Let's look at this, that initially the area of a certain block is A1, and which is at T1 degree Celsius. We are going to heat it up, and now at the temperature T2 degree Celsius, this area will be like this. So, so we can say that it is defined as, it has been defined by the B, it has been denoted by B, and it is defined as the increase in area of a solid, which is equals to delta A. It's a change in area of a solid per unit original area. Let's say original area is A, multiplied by per unit rise in temperature. Let's call it theta. So this beta is equals to delta A by A into delta theta, where delta A, it is just the change in area, and area, it's an original area. Delta theta, it's a change in temperature. I hope this all things are clear. Is it? So let's look at this. A same thing one more time. If area 1 and area 2 are the areas of a solid at different temperature T1 and T2 respectively, then coefficient of areal expansion can be defined as beta, that is equals to alpha A2 minus A1 divided by A1 into bracket T2 minus T1, and the SI unit of beta, again it's a Kelvin inverse, or the CGS unit, it's a centigrade inverse, and the dimensional formula of the beta, it's an Kelvin inverse. I hope this is clear. Is it clear? So this is the certain calculation. Its final area would be equals to A2 is equals to A1 into bracket 1 plus beta into bracket T2 minus T1. Final change in area, it's a delta A. This is equals to beta into A1 into bracket T2 minus T1. All this has been derived from this only. It's a beta is equals to delta A into A delta T. Yes, so all this has been derived from this. Final temperature could be written like this. A change in area could be written like this. And the percentage of fractional change in area, it's a delta A by A multiplied by 100, which is equals to beta into delta T into 100. I hope this is clear. Is it clear? Is it clear? Are you sure? Now let's look at certain applications based on this. First, let's say the diameter of a metal ring, let's say is D. It is something like this. This is the metal ring and its a diameter. Its diameter is D. And the coefficient of areal expansion is beta. If the temperature of the ring is increased by 1 degree Celsius, then so as we know that as it is going to be heat up something like this, and due to this heating effect its area would be increased, and when area is increased, this is beta is equals to delta A by A into delta T. So delta A is equals to beta into A into delta T, and its area, it is equals to pi r square into beta into delta T. But I have been given that delta T is equals to 1 degree Celsius change. It's a delta T is equals to 1. And if I write this based on their diameter, this radius r is equals to d by 2, and it's a r square, it's a pi d square by d square beta by 4. So increase in the area, it's a pi d square alpha by 2, because we know that beta is equals to 2 alpha. If you don't know this, we are going to derive this, don't worry. I hope this is clear. Is it clear? Now we have two different kind of bodies. uh, One of them bodies could be said as the anisotropic solids, and the other are the isotropic solids. When I say isotropic all solids, that means their xyz are equal in dimensions. But for anisotropic solids, it is quite possible that their xyz are different according to the dimensions. So for anisotropic solids, if alpha x, alpha y, and alpha z are the coefficient of linear expansions along x, y, and z directions respectively, then the coefficient of areal expansion, this could be written as beta is equals to 2 by 3 into bracket alpha x plus alpha y plus alpha z. And for isotropic solids, this beta should be equals to twice of alpha. I hope this is clear. Is it? Now let's look at certain quick questions. It says that the increase in area of a solid, it's a delta A, per unit original area, let's say divide by A, per unit rise in temperature delta T is called blank expansion of solids. Yes, this is beta, which is areal expansion of the solids. Same way, what is linear expansion of solid? It's a delta A by L delta T. This is equals to alpha. This is linear expansion of solids. Cubical expansion of solids, we are going to see it in the next slides. But before we go to it, first look at the next question. The SI unit of beta. Yes, it's a Kelvin inverse. The SI unit of alpha as well. It's a Kelvin inverse. As well as it is degree Celsius inverse. But if they have not mentioned SI, as they have mentioned SI, I could not write it's a degree Celsius inverse. Yes, I hope this is clear. Great. Next, the dimensional formula. The dimensional formula of areal expansion beta. This beta is equals to delta L by L delta T. For dimension wise, this 2 has been gone, meter, and this is equals to 1 by Kelvin. So this is equals to m0, l0, t0, k to the power minus 1. I hope this is clear. This would be the correct answer. I hope this is clear. Any doubts up till now? Is there anything? Is there anything? No? Great. Now let's look at the third expansion. It is basically the cubical expansion, or it's an volumetric expansion. Let's look at this. Let's suppose you have one of the cube at T1 degree Celsius and you are going to heat it up. When you are going to heat it up, a new volume of cube will be something like this. This is V1, this is V2. And when I say this is V1, it was at T1 degree Celsius. This is V2 when it is at T2 degree Celsius. So, so we can define an coefficient of volume expansion or cubical expansion. We represent it as in gamma, that is equals to, it is defined as the increase in the volume, I said delta V, of a solid per unit original volume per unit rise in temperature. So gamma is equals to delta V by V into delta T, where delta V, it's a change in volume. This is change in volume. V is the original volume. It's an original volume. And delta T, it's a change in temperature. I hope this is clear. Yes. So, so let's write it down. It's a V1 and V2 are the volume of a solid at temperature T1 and T2 respectively. Then coefficient of cubical expansion. This is coefficient of cubical expansion can be given as this gamma is equals to V2 minus V1 divide by V1 into bracket T2 minus T1, or I should say this, that you should remember this gamma, that is equals to delta V by V into delta T. SI unit, SI unit of gamma, again Kelvin inverse. CGS unit, it's a centigrade inverse. Dimensional formula, it's in Kelvin to the power minus 1. Final volume could be written as V2 is equals to V1 into bracket 1 plus gamma into bracket T2 minus T1, which is a change in temperature, or the final temperature could be calculated from this. Change in area, it's a delta V is equals to gamma into V into T2 minus T1. Percentage change in volume, that is equals to delta V by V into 100, and that could be written as gamma into bracket T2 minus T1 into 100. Again, we have three kinds of solids for anisotropic solids. For anisotropic solids, let's say alpha x, alpha y, and alpha z are the coefficients of the linear expansions along x, y, and z directions. Then the coefficient of the cubical expansion, this is equals to, it's an alpha x plus alpha y plus alpha z divided by 3. And for isotropic solids, gamma is equals to 3 alpha. Yes. Now let's derive this relations, because I might get confused that do you have studied this in your theory classes or not. But let's have a look. That this is the relation between alpha, beta, and gamma. So one thing let's understood, that let's suppose this is a square plate. This is a square plate and its area would be L by L. Its sides are L by L. So what I understand is that area is equals to L square. From this I can write like this. It's a delta A by A. This is equals to 2 into delta L by L. And when I write this, it is something like this. It's a delta A by A into delta T. This is equals to 2 into delta L by L into delta T. What I have done here is I have divided this both the sides by change in temperature. When I have divided this both sides on the change in temperature, this delta A by A delta T could be written as beta, and this delta L by L delta T, this delta L by L delta T could be written as alpha. So this is beta is equals to 12. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's suppose we are having one of the cube, something like this. This cubes is having a sides of L, L by L by L. So what I can write, it's the volume is equals to L cube. And when I say volume is equals to L cube, this is delta V by V is equals to 3 times of delta L by L. If I can write this, I understood this that delta V into V delta T. This is equals to 3 times of delta L by L delta T. This delta V by V delta T could be written as gamma is equals to this delta L by L delta T could be written as alpha. So this gamma is equals to 3 alpha. We have two relations that beta is equals to 2 alpha and gamma is equals to 3 alpha. I hope this is clear. Is it clear? Is it clear? So let's summarize the relations, that these are the relations between alpha, beta and gamma. It's beta is equals to 2 alpha, gamma is equals to 3 alpha. We can also write like this, it's an alpha plus beta is equals to gamma, because this is a one dimension, this is two dimensional, and this is three dimensions. This can be written, it's an alpha plus beta is equals to gamma, or I should say it's an alpha is to beta is to gamma, and this is equals to 1 is to 2 is to 3. Or a same thing can be represented something like this, it's an alpha by 1 is equals to beta by 2 is equals to gamma by 3. This is much easier, this makes things much easier when I need to compare two different quantities. And the value of the alpha, beta and gamma are independent of the units of length, area and volume respectively. I hope this is clear. Is it clear? So these are the basics. These are the basics of the linear, aerial and superficial expansion of the gases. Now, now let's look at the applications of thermal expansion. I'm going to use the every expansion. We are not going to differentiate this, that these are the applications of linear expansion or aerial expansion or cubical expansion, but this all are the very good applications. And these are the applications which can be filled very easily, because this all are the day-to-day applications of linear expansions or aerial expansion or cubical expansion. So please have a look and focus on this. So let's begin with the applications. First, change in the length. Change in the length in pendulum clock. I hope you understood this, that this is the pendulum clock, or I should say this is the pendulum, and this pendulum is having a time period of t is equals to 2 pi root of L by G. So I should say when temperature changes, length of pendulum can change. Yes, generally this is metallic pendulum. In most of the pendulum clocks, these are the metallic pendulums. And when this is metallic pendulums, that means a length of the pendulum can change. You might aware that this L is the length of the pendulum. This is the length of the pendulum, and this G, it's an acceleration due to gravity. This is acceleration due to gravity. So due to change in temperature, G would not change, only the length of the pendulum is changed. So let's understood that what I need to do is this T is directly proportional to the root of L, and this could be written as delta T by T is equals to 1 by 2 into delta L divided by L. Now we have the relation of alpha, which is equals to alpha is equals to delta L by L into 1 by delta T. So this delta L by L could be written as alpha into delta T, when I write this, I could have this relation. This is alpha into delta t. But let's write it here a delta theta so that there is no confusion between two different times. Let's write it delta theta. So this is alpha into delta theta is equals to half into delta L by L. So this change in length could be written as is equals to delta T by T. So this delta T by T could be written as 1 by 2 into alpha into delta theta, because this delta L by L could be written as alpha into delta theta. This delta T, it's a change, it's a change in time period. This T, it's a original time period, and this alpha is the coefficient of linear expansion. It's a coefficient of linear expansion of of material of pendulum. Did you get this? Are you sure? Are you sure? So we are having this relation that delta t by t, that could be written as 1 by 2 into alpha into delta theta. This is the situation. Now please do understood this very carefully. If we have calibrated a pendulum clock, if we have calibrated the pendu the pendulum clock at 20 degrees Celsius, and let's say we shift this clock, we shift this clock to a room having temperature of 30 degrees Celsius. Now what will happen to this clock? Now first, what do you understand by we have calibrated a pendulum clock? What do you understand here the meaning of calibration? So when I say we have calibrated a pendulum clock at 20 degrees Celsius, that means it can give the correct reading. It can give the correct reading at 20 degrees Celsius. But now it has been shifted to a 30 degrees Celsius. That means change in temperature delta theta is greater than 0. It's a 30 minus 20, which is basically a 10. That means you have shifted your clock to more hotter region. Now what will happen is that we understand that delta L by L is equals to alpha delta theta. As delta theta increases, delta L will increases. If this is increases, we have this relation delta t by t, it's in half into alpha into delta theta. Yes, so if this is increases, delta t increases. If delta t increases, what does it mean? Does your clock become fast, or does your clock become slow? What will be the situation? What will be the situation? Understood this very carefully. What would be the situation? We have this situation, it's a delta t by t is equals to half into alpha into delta theta, and I have increased the temperature, that delta theta is increases. As you understood that for a particular material, alpha is constant, half is always a constant. This is total time. Let's suppose for a one day 24 hours is fixed, for one day number of seconds are fixed, so t is fixed. So what I understand is if delta theta increases, delta t increases. But what does it mean when I say that delta t increases? What does it mean? What does it mean? Does it become fast or does it become slow? What would be the situation? Think by yourself. Think by yourself. What is the situation? Or if you cannot have it, let's understood this from this. It's a t is equals to 2 pi root of L by g. As length increases, because temperature increases, this time period is going to change. This t is going to change. When I say this t is going to change, please do look at this carefully. This is pendulum. Let's say it can move from here to here. Let's understood that in reality it should go from here to here and in one way, and let's say from on this way. This should be done, let's suppose this t initial should be done in, let's suppose, 2 seconds. This all are the data and this all are the figures for the understanding purpose only. So let's suppose this was the 2 seconds initially when I say at 20 degrees Celsius. Now this at 30 degrees Celsius, because it has been shifted to a new room having a temperature of 30 degrees Celsius. Now this final temperature at that time, this T increases. That means this will be done in 3 seconds. So every time it is going to take one more seconds, which it can be done in 2 seconds. So at the end of the day, when let's suppose understood that I will end my day at 12 in the night, then when the day has been over, when it's a 12 in night, my clock might have 11 or 11:30 only. Why? Because it is taking more time compared to what it should take. I hope this is clear. So if delta theta is greater than 0, your clock is slower, and when your clock is slower, you should understand that you are going to lose seconds or minutes or hours. Now let's discuss here only that second case. If delta theta is less than 0 if delta theta is less than 0, then what would be the situation? So if delta theta is less than 0, the situation is that let's suppose initially it was at 20 degrees Celsius and then it has been shifted to the 10 degrees Celsius. So it's a delta theta is less than 0. So if delta theta is less than 0, this decreases. When this L decreases, this temperature with this time will decreases. If initially it was at 2 seconds, now this will be done within, let's say, 1.5 seconds. So if it is going to do this in 1.5 seconds, it is going to do this in 1.5 seconds. That means your clock is faster, and if your clock is faster, you are going to gain seconds or minutes or hours. I hope this is clear. When to gain, when to lose. So we have the relation that delta t by t is equals to 1 by 2 into alpha into delta theta. This is the relation. This is the relation which will give me the calculation that how many seconds is to be lost or how many seconds is to be gained. I hope this is clear. Is it clear? Is it clear? So delta theta greater than 0, clock will become slower, and you are going to lose seconds. If delta theta is less than 0, clock will become a faster, and you are going to gain certain seconds. I hope this is clear. Have you got this? Have you? Are you sure? Anything that you don't understand up till now? Is there anything? Is there? So are you ready for the one of the questions based on this? Let's look at this question. A pendulum clock has been calibrated for let's say 25 degrees Celsius, has been shifted to first room having temperature of 20 degrees Celsius and second room having temperature of 40 degrees Celsius. Find number of seconds gain or lost per day. Alpha of pendulum clock. It's alpha of material of a pendulum basically, which is equals to 1 into 10 to the power minus 5 degrees Celsius inverse. So go through the data once. They have said that it has been calibrated at 25 degrees Celsius, so it can give a correct observation and correct output at 25 degrees Celsius. And now this clock has been shifted to a room having temperature of 20 degrees Celsius. And in the second case, it has been shifted to a room having a temperature of 40 degrees Celsius. So what I need to do, I need to find out number of seconds gain or lost per day, and alpha of the clock, that means alpha of the pendulum material, has been given. So let's first shift it to the room having a temperature of 20 degrees Celsius. So what I need to do is it's a delta L by L, which is equals to half into alpha into delta theta. So it's a 1 by 2 into alpha. Alpha is 1 into 10 to the power minus 5. Now its initial temperature, theta initial or theta should be, it's a 25 degrees Celsius, and theta final should be a 20 degrees Celsius. So I understand that in this situation I am going to decrease the temperature, and if decrease this temperature, this will be the faster. Yes, so that decision could be taken from here, that if delta theta greater than 0, if delta theta greater than 0, it would be a slower, and if delta theta greater than 0, it will be a faster. If it is slower, it is going to lose certain seconds. If it is faster, then it is going to gain certain seconds. So answer of going to lose the second or going to gain the seconds will be taken from this. And how many seconds is going to be lose, how many seconds is going to be lose, or how many seconds is going to be gained, that would be divided by this. It's a delta t by t, it's an half alpha delta theta. Here delta theta is 5, this is equals to delta t by t, which is a total number of seconds per day. How many seconds per day? It's an 86400. I hope you remember this. It's a delta t which is equals to 5 into 10 to the power minus of 5 multiplied by 864 into 10 to the power 2 divide by 2. I hope this is clear. Is it clear? Is it clear? This 2, this 864, it's a 432, and this is equals to 432 multiplied by 5, which is a 2160 multiplied by 10 to the power 2 multiplied by 10 to the power minus of 5. If I try to solve it further, this is 216 multiplied by 10 to the power 2 here, 10 to the power 1 here, it's a 10 to the power 3 here, it's a 10 to the power minus of 5, this is 10 to the power minus of 2. So this delta t is equals to 216 divided by 100, which is equals to 2.16 seconds. So this is going to lose 2.1 seconds per day. This is going to lose 2.16 seconds per day, because It has been shifted to a colder room. It has been shifted to a colder room. I hope this is clear. Yes, this is not going to lose, this is going to gain because it's a delta theta is less than 0. Look at this, 20 minus 25. I hope this is clear. So it is going to gain 2.16 seconds per day. I hope this is clear. Now, let's work for the second question. The second question was that initially it was at 20 degrees Celsius. No, initially it was at 25 degrees Celsius. Sorry. Initially it was at 25 degrees Celsius and finally look at this. Initially it was at 25 and finally it has been shifted to a 40 degrees Celsius. This is 4040. In this case, delta theta, which is equals to 40 minus 25, which is equals to 15 and which is greater than 0. And when it is the situation of greater than 0, when it is a greater than 0, it is going to lose a seconds. How many seconds that I need to calculate, but I'm sure that it is going to lose something. So this could be written as it's a delta t by t. This is equals to 1 by 2 multiplied by alpha into delta theta. This delta t by 864 multiplied by 10 square. This is equals to 1 by 2 multiplied by alpha. This alpha could be written as it's a 1 into 10 to the power minus of 5 into delta theta, which is equals to 15. So from this this delta t is equals to 864 multiplied by 10 to the power 2 multiplied by it's a 15 into 10 to the power minus of 5 divided by 2, which is equals to it's a 432 multiplied by 15 multiplied by this 2, this 864 has become 432 multiplied by 15 into 10 to the power minus of 3. When I do this, it's a 432. It's a 432 multiplied by 15. What it would be? Let me do this. It's a 432 multiplied by 15, which is a 6480. So it's a 6480 multiplied by 10 to the power minus of 3, which is 648 divided by 100, which is equals to 6.48 seconds. So it is going to lose 6.48 seconds per day. This will be the situation. I hope this is clear. Is it clear? Is it? Are you sure? Any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Great. So do you understand this application completely? Have you? Have you got this? Great. Let's move to the next application. Let's suppose understood that if this is a square plate and this square plate is having a, let's say, hole like this, and this is going to be heat up from this, something like this. This is the initial situation. What should be the final situation? They said this, or they asked it, that does the area of hole increases or decreases? What do you think? What happens? What will be the situation if you heat up the square plate, and what happens to this size of the hole? They said area. That means if radius is increases, area definitely increases, and something like this. So when you heat up, the thing will something like this, that first thing, its area of square plate increases. It is something like this. I am giving all you examples, and all this drawing is for understanding purpose only. In reality, this area cannot become this much by just hitting it up. This is the exaggerated form. I hope you understand this. Great. And even this all, when this square plate has increases, even this whole is going to be increases. I hope this is clear. So square plate as well as size of the hole increases, size of the hole increases if we increase the temperature. I hope this is clear. One more thing, when you don't have a feel that how this happens, how what could be done, what you understand this, that always remember this thing, always remember this thing, that thermal expansion and photographic expansion, it's a photographic expansion, behaves in a same manner. This both will behave in a same manner. When I say photographic expansion, what you need to do is, if you don't feel it that no sir, this is not the case, when I'm going to heat up the square plate, how I should come to know that this circular disc or this circular hole will increase. So what you need to do is that take your mobile phone, capture one of the image, and when you just capture the image by your fingers, now just zoom in. So when you zoom in it, you must understand that every pixel is going to zoom in. It is not the case that only certain section is going to be zoom and the other will be the same or other will be the decrease. I hope this is clear. When you zoom in it, every pixel, every detail of that image is going to be zoomed. And when every detail of that image is going to be zoomed, so it is the same case of the square plate as well, that when this square plate is going to be zoom in, yes, it has been increased in its area. Even this radius, let's say this is Ri, then this should be the Rf, and you can see it that Rf is greater than Ri. Radius is increases, area definitely increases. I hope this is clear. Is it clear? Same question on same line is that, let's suppose this is one of the cube and this cube is having a cavity at its center. If I'm going to hit this up, if I'm going to hit this up, what will happen to the cavity? So the question is, what will happen to the cavity if cube is being heated up? So what is your answer? Does it increases or does it decreases? What will happen? What I understand is this is the obvious situation. Again, a hexagerated form. It is something like this. This cube will become this much, and this is become something like this. So it's an volume of cavity increases. Volume of cavity increases if we increase the size, or if we increase the temperature, sorry. I hope this is clear. Is it clear? Is it any doubts? Is there anything, any doubts up till now? Is there anything? Is there? No? So shall we move to the next applications? Shall we? Sorry. So let's look at this next application. Let's suppose we have certain annular disk. I hope you understand annular disk. It is something like this, that this radius is the R1, this radius is the R2. Only this are the annular disk. When I say annular disk, I mean this has been filled by this, by on this section only, on, and this inner section is the hollow one. This is what we call as an annular disk. And when the situation is something like this, then, and when I'm going to heat up, when I'm going to heat up, so they will ask me that what will be the new radiuses if this annular disk is being hit up, it's being heated up. So what happens? Which one will increase, R1 or R2, or both, or none? What do you think? What do you think? What will be the situation? Which one will increase? What do you think? So when I understand this, I understand that this both is going to be increased. And when I say this both are going to be increased, I must say this R1 dash, this is equals to R1 into bracket 1 plus alpha into delta theta. And this R2 dash, this R2 dash should be equals to R2 into bracket 1 plus alpha delta theta. So this would be the situation. This is the situation for R1 dash and R2 dash. I hope this is clear. Is it clear? So this both are going to increase and nothing is going to decrease. So annular disk will increase its dimension and both the radiuses will increases. I hope this is clear. Is it clear? Is it? Are you sure? Ready for the next application? Are you ready? Are you? Great. Let's look at the next application. Let's suppose understood that this is the platform and this platform is being rotated in this manner. This is the radius of r and this is rotating with angular speed of omega. The question says that if this platform is being heated by delta theta degree Celsius, what will be new omega dash? When I say what will be new omega dash, I mean omega dash is equals to omega, or omega dash is greater than omega, or omega dash is less than omega. This is only my requirement at this point of time. So the situation is, they said that this is the situation that I'm going to hit up this, and when, let's understood that when I'm going to heat up this, what happens, that this angular speed increases or this angular speed decreases, or it does not have any impact, of on this angular speed. What will happen? What do you think? What do you think? How this could be evaluated? Is there anything in your mind? Is there anything in your mind? What do you think? What is your thought behind this? What do you think? What can be written? Yes. What is going on? Yes. What I understand is in this situation, no torque is acting on the system, And when I say no torque is acting, when I say no torque is acting on the system, that means I mean this L is equals to I omega, and that would be equals to constant. So if temperature increases, if temperature increases, I, that is what we call it's a moment of inertia. It's a moment of inertia increases, and so that if I increases, its angular speed, its angular speed will decreases. It is as simple as that. So first thing, omega dash will be less than omega. Is it clear? Now if I have been asked that what would be the change in moment of inertia, or what would be the change in omega dash, so what I can write is that the change in moment of inertia to the original moment of inertia, this is equals to beta times of delta theta. This is delta I by I, which is equals to beta times of delta theta. So when I say it's an I omega is equals to constant, I should write it's a delta I by I plus delta omega by omega. This is equals to 0. And when I write this, it's a delta omega by omega, that is equals to minus of beta times of delta theta. This minus represents that if I increases, then omega decreases. I hope this is clear. Is it clear? This is a very good application. Now you understand this, that physics is always a multi-conceptual subject. It is going to take a concept from every older units. Yes, mainly from the mechanics. That when we used to study mechanics, I always says that this is the heart of a physics. And all the medical aspirants understand that it is only the heart which pumps a blood to an every unit. So it is the mechanics which pumps a concepts to the every part of physics. I hope this is clear. Is it clear? So it is always there. Mechanics would be there every time, each time. Certain concepts would be definitely would be there, which involves mechanics. I hope this is clear. Do you understand this? Do you understand this? Are you sure? Are you sure? Great. Now let's look at the next applications. Let's have a look. Let's suppose understand that this is a mm, let's understood that this is table of length 10 meter, and I am measuring this with this measure tip, and this table is made up from the wood. It's a wooden table. Why wood? Because it does not have an impact of temperature differences, because wood is the poor conductor of heat, that you understand. And now this is measuring tape. This is measuring tape. It's a, let's understood, or let's call it, it's a made up from the steel. And this measure tape can give, this tape is calibrated at, let's call it 20 degrees Celsius. Now they will ask me that what happen if we measure this table at first 30 degrees Celsius and second 10 degrees Celsius. So this is the question, that this wooden table is there. I have given this table length of the table so that you can have a conclusion that whether it is increasing or whether it is decreasing. That one thing is for sure, that table of length is not going to be changed because this is wooden table. But this measuring tab which is made up from the steel, it is going to be changed, and when it is going to be changed, it will represent a certain error in its measuring capability. I want to analyze that only. I hope this is clear. Is it clear what I want? Okay, great. So what happened is that you must understand that this is the situation at 30 degrees Celsius. So as it has been calibrated, as it has been calibrated at 20 degrees Celsius, you are measuring at 30 degrees Celsius, your delta theta is greater than 0. So length of the measuring tap will increase. But when length of the measuring tap will increase, the situation would be something like this. Let's say this is the table, and now my measuring tap has something like this. Yes, because it is having an expanded. This is of 10 meter by my measuring tap. So maybe here, this is all for the understand purpose. Please do not understood that this is the correct figures. No, these are not. This is just the purpose of understanding. So this could be 9.8 meter, could be. So in actual this is of 10 meter. This is the actual length, and this 9.8 meter, this is the measured length. I hope this is clear. Is it clear? So it means if delta theta is greater than 0, you will have length which is shorter than actual length. I hope this is clear. Now how could I calculate that? What would be the error? Again the same thing. The error could be calculated as delta L by L is equals to alpha into delta theta. It is as simple as that. Ask them about the alpha, ask them about the delta theta, and you will have an answer. I hope this is clear. Is it clear? So this is the original length. In this case, in my case, it should be a 10 meter multiplied by alpha multiplied by delta theta. Have you got this? Have you got this? Are you sure? Now let's look at, because two questions were there. They want at 10 degrees Celsius as well. So in the second situation, that now theta final, it's a 10 degrees Celsius. Theta initial, it was calibrated at 20 degrees Celsius. So now delta theta is less than 0. When delta theta is less than 0, I mean that this was the table, and this table is if of length 10 meter. This is actual length. This is the actual length. And now when I have been measured it from the scale, now the scale would be something like this. It is something like this. So for scale, this is 10 meter and this is addition of this. Let's call it this is of 10.2 meter. Yes. So this is the measured length. This is the measured length, and this was the actual length. So from this I understood that if delta theta is less than 0, you will have a length. You will have length which is greater than the actual length. I hope this is clear. Is it clear? Is it? Do you understand this? Yes. So in this situation, again the error could be calculated using delta L by L, which is equals to alpha delta theta. So what is the error or what amount, that means the number, can be calculated from here. But whether it would be a shorter or whether it would be a greater, that decision will be the pure based on the concept. I hope this is clear. Is it clear? Is it clear? Now, do you understand each and everything up till now? Is it clear? Are you sure? Are you? Any doubts up till now? Is there anything? Is there anything? Are you sure? Now, now let's look at the one more variation, which is a variation, which is a variation of a density of a substance with temperature. It's a change in the density due to change in the temperature. So what I understand is that the volume of a solid increases on heating while its mass remains the constant. We understand that this mass is equals to volume into density. So when I'm going to heat up the device, or when I'm going to heat up the substance, its mass remains the constant but its volume is going to change. And hence, if volume is going to change but this is to be constant, this is going to be changed. Its density of the substance must increases because mass is going to be increases. So let's understood that a solid is there, and that solid is having a mass m, and it is having a volume of v1 and v2 at different densities that are at the d1 and d2 at temperatures of T1 degree Celsius and T2 degree Celsius respectively. Then what I can have is the mass is equals to volume 1 into density 1, and that could be equals to V2 D2. So it is the case that V1 D1 is equals to V2 D2. V1 is the initial volume, D1 is the initial density, V2 is the final volume at temperature T2 degree Celsius, and D2 is the density at T2 degree Celsius. Now from this I understood that I know this, that V2 is equals to V1 into bracket 1 plus gamma T2 minus T1, and when this is the situation, let's put up the value. It's a V1 D1 is equals to V1 into bracket 1 plus gamma into bracket T2 minus T1 into D2. From this I can cancel out this. It's a V1 could be cancelled out, and this D1 is equals to D2 into bracket 1 plus gamma into bracket T2 minus T1. I hope this is clear. This could be written as gamma is equals to D1 minus D2 upon D2 into bracket T2 minus T1. Or I should say that this, if the solid is heated from 0 degree Celsius to T degree Celsius, then its density could be changing from d naught to dt, and this could be written as gamma is equals to d at 0 degree Celsius minus density at T degree Celsius divided by density at T degree Celsius into T. So this is D at 0 degree Celsius, which is equals to dt into bracket 1 plus gamma into T. I hope this is clear. One more thing could be done with this. One more thing could be done with this. That let's look at this. This is density at 0 degree Celsius, and this is density at T degree Celsius into bracket 1 plus gamma T. I hope this is clear. Is it clear? So from this I can write like this, that this was the situation. Look at this. It's a density at 0 degree Celsius is equals to density at T degree Celsius into bracket 1 plus gamma into T. From this it could be written as dt is equals to d naught into bracket 1 plus gamma into T, and from this could be written as this is 1 plus gamma into T to the power minus of 1. We can apply the binomial expansion over here, and if I can apply the binomial expansion, this is 1 minus gamma T. So as temperature increases, density decreases. I hope this is clear. This is according to the binomial expansion. According to the binomial expansions. I hope this is clear. So this is the variation. This is the variation of the density when we increase the temperature. I hope this is clear. Is it clear? Is it? Are you sure? So would you like to have certain quick questions? Let's have a look. The question says that the CGS unit of cubical expansion, CGS unit of cubical expansion of solid gamma, it's a centigrade inverse. If they have been asked about the SI unit, if they have asked about the SI unit, then it would be the Kelvin inverse. I hope this is clear. Next, a dimensional formula of gamma. It's an M0 L0 T0 K to the power minus 1. This is even the dimensional formula of alpha. This is even the dimensional formula of beta. Now, next, for isotropic solids, this gamma is equals to 3 alpha. We have this relation alpha divided by 1 is equals to beta divided by 2 is equals to gamma divided by 3. From this, all the relations can be derived. Next, let's look. It's a volume of a solid. Volume of a solid increases on heating while mass remains the constant. That's a density. Yes, density decreases, and that decrease in density, this is could be given as density 2 is equals to density 1 into bracket 1 minus gamma times of delta T. I hope this is clear. Is it clear? Do you understand this up till now completely? Do you have any doubts? Is there anything? Is there? No, no. Let's discuss a very interesting variation. It's a variation in force of buoyancy due to change in temperature. Let's discuss this. It's a variation in the force of buoyancy due to change in temperature. So the situation is this force of buoyancy could be written as that Fb is equals to V in into density of liquid into G. So the situation is that when I change the temperature, if temperature changes, there is a change in V and density of liquid. So Fb, it's a force of buoyancy, also changes. I hope this is clear. So what I need to do is that let's call it Fb dash. This is equals to V dash into density of liquid dash into the G. So this V dash, that could be written as V multiplied by 1 plus gamma of solid into delta theta. This density of liquid could be written as density of liquid into bracket 1 minus gamma of liquid into delta theta, and this G remains the as it is. This is Fb dash. So if I write to solve this a little, this could be written as this is V into density of liquid into G multiplied by 1 plus gamma of solid into delta theta into bracket 1 minus gamma of liquid into delta theta. This V into density of liquid into G, look at this. This V into density of liquid into G, this is the previous force. It's a Fb. So this is Fb dash, this is Fb into bracket. Let's multiply this. This is 1 multiplied by 1. It's a 1. 1 minus this. It's a minus of gamma L into delta theta. Now it's a plus gamma s delta theta into 1. This is plus gamma s into delta theta. This is plus minus minus gamma s into gamma L into delta theta square. But as I know this, that this delta theta is much smaller amount. So it's a very small amount. So we are going to ignore this. Just ignore this. And when I ignore this, this could be written as this Fb dash is equals to Fb into bracket 1 plus gamma s minus of gamma into L into delta theta. So the situation will be if gamma s, it's a volumetric expansion of solid is greater than gamma L, volumetric expansion of that liquid, then FB dash will increase. If gamma of solid is less than gamma of liquid, practically this is not achievable in most of the cases. In most of the cases this is not achievable practically, but there are certain materials that have this property that gamma s is less than gamma l. It could be done. So in this case FB dash will decreases, and if gamma of s is equals to gamma of l, if gamma of s is equals to gamma of del, that's then FB dash will be same. I hope this is clear. Is it clear? Are you sure? Are you sure? Do you understand this completely? This is very pretty application. Please do remember this. Please do remember this. This is very useful application for us. I hope this is clear. Is it clear? Is it clear? So ready for the next questions? Ready? Let's have a look. Let's suppose understand that. Suppose this is one of the road and this length is L1. This is another road and this length is L2. Suppose this road is heated up by certain temperature delta theta. If this road is being heated up by using same temperature difference, it's a delta theta. So the question says that find out, that's one more thing, it is having an temperature coefficient of alpha 1, this is having a temperature coefficient of alpha. To find out relation between length and alpha so that difference of lengths of this roads, difference of lengths of this roads are independent of of temperature. So we need to find out a relation so that between the length and alpha, so the difference of lengths of this roads are independent of the temperature. So what they want is, let's understood this, they want L2 minus L1. As I could see, this L2 is greater, is equals to L2 dash minus L1 dash. This was at initial temperature and this is the situation after temperature has been raised. So this could be written as L2 minus L1, this is equals to L2 dash, which could be written L2 into bracket 1 plus alpha 2 into delta theta minus of, it's an L1 into bracket 1 plus alpha 1 delta theta. So this could be written as L2 minus L1 is equals to L2 plus L2 alpha 2 delta theta minus L1 minus L1 alpha 1 delta theta. So from this this L2 minus L1 and this L2 minus L1 could be gone, and if this has been gone, this is something like L2 alpha 2 delta theta is equals to L1 alpha 1 delta theta. So from this I can write like this, it's an L2 alpha 2 delta theta, this is equals to L1 alpha 1 delta theta. I should write like this, it's L2 alpha 2, this is equals to L1 alpha 1, or I should say L into alpha should be constant. If this is being achieved, if this is being achieved, then the difference of their lengths, what I want, I don't want that this length is not going to change. No, it is not like that. If this length is L2 and it is being heated up by certain temperature, it would be definitely increased. That I understand. Even the same is for here. So I don't want that this length is not going to change. I want the difference of their lengths is not going to change. I hope this is clear. Or it should be the same. It should be same at every temperature. So this can be achieved. This can be achieved if this can be done. It's an L2 alpha 2 should be equals to L1 alpha 1, or I should say it's an L into alpha is equals to constant. If this is the case, this can be achieved. I hope this is clear. Is it clear? Any doubts up till now? Is there anything? Is there? No? Great. So let's just wind it up this session over here. This was all about the expansions of solids. Please do this very carefully. This is having a very high probability to be asked in the every competitive examinations. Please practice a lot this kind of questions. First, this is a very easy kind of questions, very easy questions. Yes, I have tried to cover as many applications as I can cover. Yes, a very few applications can be outside to this, but you must have a command over this applications first to make it correct. I hope this is clear. Please practice a lot. This will save us. Thank you. Have a good day. Take care.